Welcome to part 3 of lecture 15. So we have our notion of regret, which is that we want to design an algorithm that no matter how the adversary picks cost vectors, will achieve, it will experience a cost or perhaps an expected cost that competes with the cost of the best action in hindsight. And the question is, how do we do that? Okay. So there are a few kind of things to notice. The first thing is that we really don't have a whole lot of information to go on other than the past performance of each of the actions, each of the possible actions. Right? So a natural strategy is to look at that past performance and look at, so far, what cost has each action experienced so far. So let's say, let's let C, the cost up till time t for each action A, be the sum of the costs experienced up to and including time t minus 1 of action A. So the idea is to select actions for which this past performance is good. Okay, have lower cost so far. And to get an idea of why this is not trivial, let's consider one algorithm that actually doesn't work very well, so a bad algorithm that kind of takes this idea to an extreme. Okay, we'll call it, so this algorithm is called follow the leader. Which we can abbreviate FTL. And what it does is at time step t, so it selects one action that is just the action that minimizes the costs at all, the sum of the costs at all previous time steps. Among all possible actions. Okay, so for this, you do this for each t. Okay, so this is, an algorithm. And it turns out that this algorithm does, it seems like a pretty natural approach, right? To just look at, what have costs have different actions experienced so far and just pick the one that has done best. And it turns out that this algorithm is actually pretty terrible. And to see why that is, so the regret of this algorithm, can be as large as 1/2. In fact, it can be higher than that, but whatever. This is good enough, even with k equals 2. Okay. In general, it can be kind of arbitrarily close to 1 as k gets big. So, why is this? Well, let's say let's look at the costs. So here's a, time going this way. And we've got two actions, 1 and 2. So C1, C2. Right. So in our first time step, we'll choose an action. We'll assign cost 1 to action 1 and cost 0 to action 2. And in general, we don't really know. It doesn't really matter how the algorithm starts off, but it will make some choice. Maybe it'll get lucky, maybe it won't. But in the next time step, we're going to flip the two costs. And, if we look at follow the leader's action at this point, we don't really know what it will do in the first time step. But in the second time step, it'll notice that action 1 did best, so it'll choose action 1. Okay. And then in the next time step, it'll go and it will choose after 2 time steps, both actions have equal cost, so it'll pick one of them arbitrarily. Let's say it always breaks ties. Sorry, here it'll choose action 2. Okay. In the next time step, let's say it always breaks ties by choosing the earlier of the 2 actions. So let's just, for simplicity, imagine we'll choose action 1. And notice that then it's paying cost 1 even though there was an action with cost 0. And again, what at the next time step, it'll look at the cost of the action. So far, action 1 has higher cost than action 2, so it will choose action 2. But then the adversary will see that coming and again put cost 1 for action 2 and cost 0 for the first action. And it'll just keep on going like that. So in each subsequent round, the follow the leader algorithm will alternate between choosing action 1 and action 2. And the adversary will also alternate between putting cost 1 on action 1 and 0 on 2, or vice versa. And it will set it that because it knows what is coming, the adversary can make sure that the achieved cost, the realized cost of this strategy is exactly t, or maybe t minus 1, depending on that first action. But then the best action in hindsight has cost t over 2. In fact, both of them have cost pretty much exactly t over 2, exactly t over 2 if t is even. And so the regret here is very high. Okay, it is in particular. It's the average regret, as we defined it, is 1/2, which is actually pretty much as high as you could really get it to be reliably. Okay, so that's not a great strategy. What can we do instead? So let's just sort of see some principles for low regret algorithms. On one hand, we do want to, we're doing something right. So we need to choose actions based on their past cost. But actually, what we really want to do is, instead of choosing, deterministically based on the past actions, what we want to do is just assign low-cost actions higher probability, and higher cost actions lower probability. Okay, but it's we still want to assign non-zero probability to these somewhat higher cost actions. So, what's a natural way to do this? How could we kind of randomize our behavior a little bit so that this type of bad example that we saw for follow the leader isn't going to happen consistently to us? So there are actually multiple ways of doing it, but the way that is that we're going to look at today is to assign probabilities that drop off exponentially in the cost so far of a given action. So specifically, what we'll do is at time t, we're going to, the probability of action A should be proportional to some exponential in the realized cost so far. Okay, so this cost of A so far, we call that like C, less than T. Okay. And then the base of the exponent here is just some number. So this eta here is some parameter that we'll call a learning rate. And when that learning rate is close to 0, then the probabilities are kind of more or less all the same. They're very when the learning rate is exactly 0, we're just picking actions uniformly. If we drive the learning rate towards 1, then we are basically doing follow the leader. We'll wind up doing something that is basically follow the leader. And in between, we're somehow interpolating between those strategies. So this idea, there are different more or less equivalent forms of it, but this idea is called multiplicative weights. Multiplicative weights. So it takes a parameter eta, and at each time step, so what it starts by doing is it assigns some initial weight to all the objects, all the actions. So at time 1, our initial weights are going to be all initialized to 1. So our initial weights are 1 for all actions between 1 and k. And then for t time steps, we do the following. Okay, so the first thing we're going to do is compute a distribution that is proportional to the weights we have so far. So we'll set zt to be the sum of all the weights for time t. And we'll set pt to be, we'll take this weight vector and we'll just divide by zt. So just to be clear, for types, the probability is like a vector, weight is a vector, the w is a vector of weights, and z is this normalizing constant. So we get a probability distribution. And at this point, if this smells a lot like the exponential mechanism, it's starting to smell like the exponential mechanism, that is not a coincidence. We'll talk about that connection later, but for now, we'll just analyze this as a standalone thing. Okay, so that's the action that D plays. Okay. So now, D plays distribution PT. It's expected, so it selects, sorry, we skipped a step here. So now the adversary selects a cost vector, CT, and D plays PT, and its expected reward, or expected cost rather, is the inner product of P and C. Okay, and then it receives. So it sees how much it paid, and it receives CT, and now it updates its weights. And the way it updates its weights is the following. So for each A, we set the weight at time t+1 of A to be the weight at time t times 1 minus eta raised to the power of the cost experienced by that would have been experienced by that action at time t. Okay, so that's our whole algorithm, and then we just repeat. Okay, so let's just double check a few things. So one is that if we look at w at time at t plus 1 of a, it started out with weight 1. And then at each action, at each time step, it gets multiplied by 1 minus eta times the cost for that time step. So indeed, after all these time steps, if I look at time t, that's the product from I equals 1 to t of like 1 minus eta times the cost at time t for a. So that's indeed 1 minus eta times the cost so far. Okay, so check, that's, that's doing what it's supposed to do. And, yeah, this view of it, this is like just a slightly more efficient implementation of that. And now what we want to do is kind of understand why this algorithm works. So again, what's going on is, if I imagine the actions on the x-axis, we've got like the actions have different costs. And if we were to draw the costs so far for each action, then the probability distribution we're drawing from assigns sort of exponentially more weight to the low cost option. Sorry, this is the other way around. It assigns exponentially higher weight to the low cost options, and then weight that decreases with as their probabilities, as their costs get higher. The experience costs so far get higher. And so as I said, this is basically like running the exponential mechanism that we've seen in the class so far. In the analysis we're going to do, our first analysis, the analysis we'll do today, we're not going to take that perspective of thinking of it as an instance of the exponential mechanism. We'll come back to that another time.